We're going to be solving Cambridge International AS in A-Levels Chemistry, Paper 1, Multiple Choice, October-November 2025, Paper 11. What is the electronic configuration of a particle of aluminum 2713 and aluminum plus? So first of all, we're going to identify the electronic configuration of a particle of aluminum 13, and then we're going to take out one electron from it. So it's going to be 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're done with the 10 electrons. Now we got to add 3 more, so it's going to be 3s2. And now we just need to add 1 more electron, so it's going to be 3p1. So over here you can count, we have exact 13 electrons. So after the 13 electrons were done, now we need to take out 1 electron because it's a positive one. So when we take out 1 electron, obviously we're going to take out electron from this shell because that's the last one. So we're going to take out 1 electron from here, and if we erase it, then this is the electronic configuration for a aluminum ion. So which makes option B the correct answer. 1s2, 2s2, 2p6 and 3s2 makes a total of 12 electrons that we need, because out of 13, 1 electron is gone. The data in the periodic table gives the 5th to 10th ionization energies of 3 elements from period 3 of the periodic table. From 5th to 10th ionization energies we're given with, and now we have to figure out what is the correct identities of the 3 elements. We need to figure out just one thing, the big jump. Where does the big jump come in the ionization energies? From 6,000 to 21,000. That's a very big jump. So over here, I'm considering this to be my big jump, right? Then from 21,000 to 25, that's just an addition of 4,000. Then 25 to 29, again 4,000. Over here it's then again 6,000, almost 6,000, then again 5,000. So over here there's the biggest jump that I can see. So I'm going to consider that element X is going to have 5 electrons in the last shell, because the first 5 electrons are being taken out from the valence shell. Why are they going to be taken out from the valence shell? Because look, from the 5th to 6th ionization energies, there's a big jump. That means the first 5 electrons from the last shell, and then the 6th electron from an inner shell. So over here, what we're going to consider, this element X is present in period 5 of the periodic table. So period 5, sodium is present in group 5 of the periodic table, not period 5, sorry, group 5, because it has 5 electrons in the last shell. So sodium is in group 1 of the periodic table, magnesium is in group 2, sulfur is in group 6, only phosphorus is in group 5. But still, just to confirm, sulfur is in group 6. So over here, over in the element Y, if we consider it to be sulfur, since we've crossed out option A, B and D, we need to consider that sulfur should have a very big jump from the 6th to 7th ionization energies if it's in period group 6. So over here you can see from 7,000 to 8,000, just a jump of 1,000, from 8,000 to 27,000. It's a big jump. So this is the biggest jump. So definitely it's in group 6, and it's going to be sulfur. And for chlorine, you're going to expect a big jump from the 7th to 8th ionization energies, because chlorine is in group 7. That means the last shell has 7 electrons, and the 8th electron is going to be taken out from an inner shell. What contains 9.03 into 10 exponent 23 oxygen atoms? So you know that over here, first we're going to figure out for option A, which is aluminum oxide. You know that 1 mole of aluminum oxide, which is Al2O3, you gotta know the formula. 1 mole of aluminum oxide has 3 moles of oxygen atoms. I guess that's unarguably the basics of moles in chemistry, that 1 mole of Al2O3 is going to have 3 moles of oxygen atoms, because the formula includes a 3 over here. So we know that 1 mole of Al2O3 is going to have 3 moles of oxygen atoms, right? So 0.25 mole of aluminum oxide, we're making aluminum oxide ratio oxygen. If you think that I'm doing a little like faster, look what I'm doing. This is aluminum oxide ratio oxygen. 1 mole contains 3 moles of oxygen. So 0.25 mole of aluminum oxide, which the question states, is going to contain x moles of oxygen, and x comes out to be 3 into 0.25. Let's see what we get. 3 into 0.25, we get 0.75 moles of oxygen atoms. X comes out to be 0.75. Now I know that my 1 mole contains 6.02 into 10 exponent 23 particles, right? So my 0.75 moles is going to contain X particles. X comes out to be 0.75 into 10 exponent 23. 6.02 into 6.02 into 10 exponent 23. And that gives me 4.515 into 10 exponent 23 atoms of oxygen. So option A is a big cross. Option B says 0.75 mole of sulfur dioxide. Now you got to make ratio. Sulfur dioxide ratio oxygen. 1 mole of sulfur dioxide has 2 moles of oxygen because the formula includes a 2 over here. That means 1 mole of this thing is going to have 2 moles of this thing. So 1 mole of sulfur dioxide has 2 moles of oxygen. So 0.75 moles of sulfur dioxide is going to have X moles of oxygen. The moles of oxygen come out to be 2 into 0.75. 2 into 0.75, we get 1.5 moles of oxygen. Now we know that 1 mole of oxygen Now we know that 1 mole of oxygen is gonna have 6.02 into 10 exponent 23 particles. So 1.5 moles of oxygen is gonna have X particles, and X comes out to be 6.02 into 10 exponent 23 into 1.5. That gives me 9.03 into 10 exponent 23 atoms of oxygen, right? Which makes option B the correct answer. You can see it again. What I just did was that sulfur dioxide ratio oxygen. 1 mole of sulfur dioxide contains 2 moles of oxygen atoms. Atoms I'm talking about. So 0.75 moles of sulfur dioxide is going to contain X moles of oxygen atoms. X comes out to be 2 into 0.75, right? That means we have 1.5 mole of oxygen atoms. 1 mole of oxygen atoms contains 6.02 into 10 exponent 23 atoms. So 1.5 moles is going to contain X number of atoms, and X comes out to be 6.02 into 10 exponent 23 into 1.5, which makes option B the correct answer. Methane and steam react to produce hydrogen. 0.80 gram of methane and 1.35 gram of steam react. Okay, so we have 0.80 grams of this methane thing and 1.35 grams of this steam thing. One of the reactants is used up. That means the other one's going to be excess. Now we got to calculate the moles of both of the things. And from that, we got to figure out what is the limiting reactant, what's in excess. So the moles of methane is going to be mass over MR. Mass is 0.80 and the MR of methane is 16. .05 moles of methane. Now for water. Moles equals to mass upon MR. Mass is 1.35 and MR of water is 18. We get 0.075 moles of water. Now we got to figure out one thing, that 1 mole of methane reacts with 2 moles of water, right? This is water and this is methane. So if we have 0.05 moles of methane, how many moles of water are we going to need? 0.05 times 2. We are going to need 0.1 mole of water. But how many moles of water do we have? We have 0.075. We don't have 0.1. We have less moles of water. That means that all of the methane is not going to react. Methane is in excess. Look. Why? Now you can reverse the ratio and see that. Now do this. You can make this ratio, CH4 ratio H2O. We have how many moles of H2O? We have 0.075. And we have how many moles of methane? how many moles of methane are going to react with 0.075 moles of H2O? If 1 mole of methane reacts with 2 moles of water, X moles of methane are going to react with 0.075. What does X come out to be? Check it for yourself. X comes out to be 0.0375. These many moles of methane are going to react, but we have 0.050. That means methane is in excess. We have more moles of methane. So water is the limiting reactant over here, and the moles of water are 0.075. You can check it for yourself. Over here, I've shown you in terms of your water that you're going to require 0.1 mole of water, but you have less water. And over here, I've shown you that you're going to require 0.0375 moles of methane, but you have more of methane. So exactly, no, methane is more, water is less, water is going to be the limiting reactant, right? Which volume of hydrogen measured at room conditions will be produced? Now we know that we always use the moles of the limiting reactant to determine the moles of the product. So if we have 0.075 moles of water, how many moles of hydrogen gas are we going to produce? Simple, make ratios. H2O ratio hydrogen. From the equation, we can see that 2 moles of H2O are going to react and form 4 moles of hydrogen. So if we have 0.075 moles of H2O, we're going to have X moles of hydrogen. So X comes out to be 0.075 upon 4 into 2. We have 0.15 moles of H2. Now we got the moles of H2. We got to figure out the volume. What do we do if we want the volume? We just multiply the moles by 24 and we get the volume. The volume comes out to be 3.6 dm cube. Which statement explains why sodium and potassium have different melting points? Remember, potassium is going to have a lower melting point than sodium because the metallic bonding in potassium is weaker than that in sodium. Why? Because in potassium, the size of the cation is greater, so the distance between the cation and the delocalized electron is greater, so the metallic bonding is weaker, whereas in sodium, the cation is smaller, so the distance between the cation and the delocalized electron is less, so the metallic bonding is stronger. The attraction between the cations and the delocalized electron is stronger in sodium. Yeah, it's stronger in sodium. The attraction between the cations and anion, there are no anions in metals. The attraction between the atoms, there are no atoms in metallic bonding. There are only cations because all the atoms tend to lose their electrons. The attraction between the nuclei and the shared pair, leave it. NH3 and HCN react together to form ammonium cyanide, an ionic compound. Which row states the number of coordinate bonds and the number of pi bonds in one formula unit of NH4CN? So we have NH4CN. We know this is nitrogen. I'm going to tell you what's going to happen in totality. So first you have ammonia with a lone pair, and you have hydrogen triple bonded to this cyanide part. What's going to happen is that this hydrogen is going to break off, and this carbon is going to get a shared pair of electrons. So now we have this hydrogen that is positively charged because basically it lost its electrons to this carbon. So this carbon, this hydrogen which is positively charged and has no electrons, because you know a positive hydrogen means it's no electrons, is going to come make a dative bond here, right? So we have a dative bond between nitrogen and hydrogen. And now since this part is made a dative bond, and we have a positively charged species over here, this entire thing is going to get a positive charge. And since hydrogen gave its electrons to this carbon, so there's going to be this negative charge on this nitrile part. Now what's going to happen? We have a positive and a negative species. So there's going to be what kind of bonding? Ionic bonding between them. So number of coordinate bonds, we only have one coordinate bond over here. Coordinate bonds are also called your dative covalent bonds. So one number of pi bonds. How many pi bonds we have? Look, the first bond in carbon and nitrogen is a sigma bond. The second bond is going to be a pi bond, and the third bond is going to be a pi bond. So we have 2 pi bonds here. So we have 2 pi bonds. When 1 mole of ethanoic acid in aqueous solution is neutralized by an excess of sodium hydroxide, the 55 kilojoules energy is released. Which statement about the reaction is correct? So we have ethanoic acid and we have sodium hydroxide. We know ethanoic acid is a weak acid and we know sodium hydroxide is a strong base, and we know that whenever we have acid plus base, we do a neutralization reaction, and in neutralization reaction we release 57.7 around kilojoules of energy, but over here we're releasing 55. We're releasing less energy. Why? Because we're using a weak acid. Whenever we use a weak acid, some of the energy that's released is used to ionize the acid. That's why. The reaction is exothermic because only bond breaking takes place. No, in exothermic reactions, more energy is released in bond breaking than in bond. More energy is released in bond making than in bond breaking. The reaction is exothermic because only bond forming takes place. No, both bond breaking and bond forming is going to take place, but what's going to happen is that more energy is going to be released in bond making. The reaction is exothermic because more energy is given out in breaking bonds. More energy is given out. Energy is never given out when you break bonds. When you break bonds, you got to give in energy. The reaction is exothermic because more energy is given out in forming bonds than is taken into breaking bonds. Yeah, that's correct. When you form bonds, you release energy. In an experiment, 1.6 gram of the fuel is burned. Okay, 45% of the energy released is absorbed by 200 grams of water. 45% energy is absorbed by 200 grams of water. The temperature of the water rises from 18 degrees to 66 degrees. What is the total energy released per gram of the fuel burned? So we know that to calculate the energy that's released, we use mc delta T. Over here, m is the mass of the water, which is 200 grams. C is the specific heat capacity, which is 4.18. And delta T is the change in temperature. Over here, we take the change in temperature. In degrees in Kelvin, it's the same. So the change doesn't change. So we can take it in degrees as well. So 66 minus 18. How much energy are we getting? 200 into 4.18 times 66 minus 18. We're getting 40128 joules of energy. Now you got to realize one thing. This is only 45% of the total energy because 45% of the energy released is absorbed. So that's only 45% of the energy that raised this much temperature. So how much energy is going to be? 100%. So if 45% is 40128, then 100% is going to be x. The value of x comes out to be 100 into 40128 upon 45 into 100 divided by 45. And that is 89137.33 joules of energy. Now this is the energy that's released by 1.6 grams of fuel. We got to find out the energy that's released per gram. That means 1 gram of fuel. So if 1.6 gram can release 89137.33, then 1 gram can release x, and the value of x comes out to be this divided by 1.6, and we get 55733.33 joules of energy, which makes option number B the correct answer. I hope you got. So now we have a question of redox balancing. Redox balancing is the easiest stuff in the entire chemistry. Like, I'm not even joking, that's the easiest thing you can get. So you're lucky if you get these equations. You're lucky. Trust me, you're lucky. I'm going to show you what we're going to do. We need to figure out AB WX, okay? People use tons of methods and I don't know what not. They make half equations of this and this, and then they make half equations of this and this. No, you don't need to do anything. Just look how easy it is. Look, you're going from Zn to Zn2 plus. What are you doing? You are losing 2 electrons. Now, when you lose 2 electrons, you have to gain 2 electrons as well, right? You got to gain 2 electrons. Now, what is happening to sulfur? Sulfur over here, it's a positive 4. Okay? You can figure it out. It's a positive 4 over here. And over here, sulfur is a 4 2s are 8. 8 minus 2, 4 into 2 equals to negative 8. And then you have a total 2 negative charge. That means you got to have a positive 6 charge. That means you got to have a positive 3 on one sulfur. One sulfur over here has a positive 3. Okay? Over here, it's a positive 4. Over here, it's a positive 3. Gain or loss? There is a gain of 1 electron. Now we need to gain 2 electrons. So we have 2 sulfurs over here. If we added 2 over here, now what is going to happen? 2 sulfurs are going to each lose are each going to gain 1 electron. So we're going to go to 3 plus over here. So we add a 2 here. Now, next step, we got to balance the oxygens. On this side, how many oxygens do we have? On this side. On this side, we have 2 into 3, 3 times 6 oxygens on this side. Over here, we only have 4 oxygens, right? Over here, we have 6 oxygens. Over here, we have 4 oxygens. And then we have some oxygens over here. So what do? It's simple. We add 2 oxygens on this side, on the more deficient side. So we add 2 oxygens over here. When we add 2 oxygens on this side, over here we had a 1. So we have 4. Now how many oxygens we get? We get 4 2s are 6. 6 over here. And 6 over here, 4 over here. So we should add 2 oxygens over here. But when we add 2 oxygens over here, the hydrogens get unbalanced. So what do? We add 2 oxygens here and 4 here. Now check. Now everything's balanced. Now we have 4 hydrogens, 8 oxygens on this side and 8 oxygens on this side. So that's how you balance out stuff. Now over here, look, manganese over here is a positive 4. Over here, it's a positive 2. So how many electrons are we gaining? We're gaining 2 electrons. One atom is gaining 2 electrons. So now some atoms need to, this manganese is getting reduced. So this has to get oxidized. So let's see. Over here, the oxidation state of sulfur is 2 3s are 6 minus 2 plus 4. Over here, it should be a plus 5. Because now we're going to add a 2 here. That means 2 atoms each going to lose 1 electron. So that's how we go from plus 4 to plus 5. And then where 2 electrons are going to be lost, then we're going to gain 2 electrons. And now what do we do with H plus and waters? Simply balance them out. How many oxygens do we have on the right side? We have 6, 7, 8 oxygens. How many oxygens on the left side? 6 oxygens. So add a 2 here. Now how many hydrogens on this side? 4. So add a 4 here. Now what do? Now which values are we getting? We're getting 4 for X, right? For W, what are we getting? Where's W? For W, we're getting 2. Then for B, what are we getting? What is B? B, we're getting 2. And for A, we're getting 2 as well. So option number B. This is how you just balance. You just look at the atoms. You just try to balance out the both sides. You balance out the electrons. That's all. Which equation shows hydrogen acting as an oxidizing agent? Oxidizing agent means itself, it should get reduced. And when hydrogen gets reduced, it means it should gain electrons. So hydrogen should be gaining electrons. Its oxidation number should reduce. So over here, hydrogen is a 0. Over here, it's a negative 1. So this is from 0 to negative 1. What is this? This is a reduction. This is pure reduction. So option number A is going to be the correct answer. 1 gram of nitrogen gas is stored in a 2 dm³ vessel at 40 degrees Celsius. What is the pressure in the vessel? We don't have room temperature. That means we cannot use any of the moles formula or volume 124. We have to use PV equals to nRT. We got to find out the pressure. We're going to rearrange the formula. It's going to be nRT upon volume. N is the number of moles of nitrogen. How are we going to figure out the moles? There is a simple formula for moles that we use. Moles equals to mass upon mR. So the mass of nitrogen is 1 and the mR of nitrogen gas, we're not dealing with only nitrogen, we're dealing with N2. So it's going to be 14 plus 14 because we have 2 atoms of nitrogen. So that's 1 upon 28. How much moles do we get? 0.0357. So 0.0357 times R, which is 8.31 times temperature, which is 40 degrees Celsius. And we have to convert it into Kelvin. So 40 plus 273, that's going to give me 313 upon my volume. My volume is in dm cube. I got to have the volume in meter cube. I got to remember these things. 2.00 into 10 raised to power negative 3. That's going to be in dm cube. So 0.0357 times 8.31 times 313 upon 2.00 into 10 exponent negative 3. And I get 4642.8.3855 pascals, which is option number C, right? If I round it off to 3 significant figures, you can see all the values are given to 3 significant figures: 2.003 significant figure, 40.03 SF, 1.00, that's 3 SF. Okay, 1 molecule of hemoglobin can bind with 4 molecules of oxygen according to the equation shown. We have hemoglobin, we have oxygen, and then we're going to form 1 mole of oxyhemoglobin, which is HbO24, when the equilibrium concentration of oxygen is 7.6 into 10 exponent negative 6 mole per dm cube. The equilibrium concentration of Hb and Hb2O4 are equal. What is the numerical value for Kc for this equilibrium? Okay, so first we're going to write the Kc expression. The Kc expression is going to be HbO24, right? We're going to take this upon oxygen concentration times 4, because we have a 4 here. We're going to take all in Kc because they're aqueous solutions, right? Multiplied by Hb. So if you try to write the equation, if we consider HbO24 to be X, we write X on the top, and then we write O2 concentration as 7.6 into 10 raised to power negative 6 times 4, and then for Hb we can also consider it to be X. Now you see it for yourself that X gets cut with X. If we do some cutting, X gets cut with X. So we have 1 upon 7.6 into 10 exponent negative 6 whole raised to power 4. What do we get? 1 upon 7.6 into 10 exponent negative 6 whole raised to power 4. We get 2.99 into 10 raised to power 20. So that's, if we round it off to 1 significant figure, to 2 SF, whatever, 2 significant figures, this 9 is going to become a 0, and this is going to become a 3, so it becomes 3.00. So that's the answer. I hope you got it. It was a little tricky, but you just had to cancel it out. Now we have a pH curve. The aqueous acid P and aqueous alkali Q have the same concentration. They have the same concentration. 20 cm cube of P is added to the conical flask. So that is my flask. I have added acid P to the flask, and I've added 20 cm cube of this acid. Q is slowly added to the flask. The volume of Q and pH are recorded. So volume of Q and pH are recorded. How much volume of Q did I? pH is this, and the volume of Q is basically this. So exactly at 10, if I see exactly at 10, my Q neutralized my 20 cm cube of acid P. Q is a alkali. Q is gonna have more OH negative ions in the same concentration. Q is gonna have more OH negative ions in the same concentration. So over here, first things first, compared to the acid, Q should have twice the amount of OH negative ions, because we need half the volume of Q compared to the volume of the acid. So this and this, because they have twice the amount of hydroxide ions. I hope you get it. That's why half the volume of the same concentration is neutralizing the acid. That's a tricky part over here. If 20 cm cube of Q would have been used, then we would say it would be NaOH or NH3. But no, now we need double the hydroxides because we're using half the volume compared to this volume, and they both have the same concentration. Next, either it's HCl or it's ethanoic acid. We know that initially the acid should have, if it has a low pH, it's going to be HCl. If it has a higher pH, it's going to be ethanoic acid. So we look, the pH is below 1. That means we're dealing with a strong acid initially in the flask. So it's going to be HCl. I hope you got it. Photochromatic glass used for sunglasses darkens when exposed to bright light and becomes more transparent again when the light is less bright. The darkness of the glass is due to the presence of silver atoms. The darkness of the glass is due to the presence of silver atoms. So these atoms are making the glass darker. So look, what are we doing? Over here, this reaction is going to have when we're going to have bright light. So we release silver atoms so that it gets darker. And this reaction is then going to happen when we have less bright light. So that what happens that it becomes like more transparent. Which statement about the reaction is correct? Cu plus 1 and Cu2 plus ions act as catalysts. Cu, we're going to see this at the end, because for catalysts, I always suggest see it at the end, because if all options are wrong, then it's got to be correct. Because oxidizing, reducing, we can do, but catalyst, it might be a little trickier. Cu plus 1 ions act as oxidizing agent in reaction 2. So they're going from plus 1 to plus 2. So they're getting oxidized. So they're acting as reducing agents. Cross. Reaction 3 increases the darkness of the glass. Reaction 3 is producing silver ions. The darkness of the glass is because of the silver atoms. So reaction 1 is going to increase, not reaction 3. Silver atoms are reduced in reaction 3. Silver atoms are reduced. So they're going from 0 to positive 1. They're oxidized. Right? They're not getting reduced, they're getting oxidized. And you can see it for yourself. Silver atoms getting an increase in oxidation numbers. So option A is correct, that copper plus 1 and copper 2 plus are acting as catalysts in this reaction. And you can see it for yourself, that they're being regenerated. Like 2 plus is regenerated, and then 1 plus is also regenerated in the last equation. Like over here 1 plus regenerated, over here 2 plus regenerated. Over here 2 plus used, over here 1 plus used. Which statements about the reaction are listed? 2 statements. Okay, the reversible reaction between methanol and ethanoic acid. What are we doing? We're doing esterification. Liquid is catalyzed by adding small volume of sulfuric acid. Sulfuric acid is a homogeneous catalyst. That's correct. Because methanol is a liquid, ethanoic acid is a liquid, and sulfuric acid is going to be liquid. All 3 liquids, homogeneous catalysis. Sulfuric acid lowers the activation energy for the reverse reaction. That's correct. Whenever you add a catalyst, it increases both the rate of your forward and the reverse reaction. Not only forward, not only reverse. Both the reactions are increased. The atomic radii and the ionic radii for 3 elements in period 3 are shown. So you can see that we know that across the period, what happens to your atomic radii? Across the period I'm talking about, it decreases because the nuclear charge is increasing, because the shielding remains constant and all that stuff. So over here we can see that this has the greatest atomic radii, this fella, and then this, and then at last this. And we know that our metals have smaller ionic radii compared to atomic radii. Smaller ionic radii compared to your atomic radii, because they lose electrons. So what happens that the remaining electrons are pulled in like more sharper. So we can see this fella has a smaller ionic radii. So definitely this is going to be a metal. Element Y, it has a greater ionic radii. So this is, I'm considering it to be a non-metal that's gaining electrons. And element Z again has a smaller ionic radii. So this is also going to be a metal. Element X has lower electrical conductivity than element Y. Element X is a metal, so it's going to have higher electrical conductivity. Element Y is higher melting point than element X. Element Y is a metal, non-metal, so non-metals have lower melting point. Element Y and element Z react to form an ionic compound. Y and Z, metal and non-metal, going to react and form ionic compounds. So I'm going to go with option C. Element Z forms ionic compound by gaining electrons. Element Z is a metal, and metals form ionic compound by losing electrons. So you just have to figure out the metals and non-metals. That's all the trick in the question. The equations are listed. X, Y, Z are whole numbers. Which equations can be balanced? Can be balanced if X equals to 4 and Z equals to 2. X equals to 4, Z equals to 2. Let's see. 4 aluminum here, 4 aluminum here, 2 3s are 6. Oxygens here, 3 here, 4 and 2 cannot be balanced. Magnesium cannot be balanced. 4 and 2. 4 sodiums here, 4 sodiums here, 2 here, and then 1. 1 and 3 can be balanced. I just balanced them in front of you. Which oxide has a simple structure rather than a giant structure? P4O10. This has a giant covalent, giant ionic, giant ionic. The trends seen in group 2 can be used to predict the properties of radium and its compounds. You know who discovered radium? It was a scientist called Marie Curie, right? She was a female scientist. Which statement is correct? Radium has the highest second ionization energy. It has the lowest ionization energy in group 2. Why? Because it's at the bottom, and the more you go down the group 2, the lower your ionization energy gets. Radium hydroxide is the most soluble. Radium carbonate has the lowest, highest. Radium reacts faster with water than other group elements. Yeah, that's going to be correct because down the group the reactivity increases. And when your reactivity is increasing, so you're going to react faster. And your thermal stability of a carbonate is going to be like a lot more than others because it's more reactive. It tends to form compounds rather than staying alone. So it's not going to decompose easily. Equal masses of calcium carbonate, calcium nitrate, barium carbonate, barium nitrate are thermally decomposed. The volume of gases, we have equal masses. Equal masses means that the most amount of moles are going to be in calcium carbonate or calcium nitrate because moles and MR are inversely proportional. Barium has greater MR, so it's going to have less moles. So if you're dealing with the moles, these are going to have the greatest moles. Calcium carbonate and calcium oxide, which compound will produce the greatest volume of gas? Firstly, we know nitrates produce more gas, and secondly, we know calcium nitrate is going to have more moles than barium nitrate because equal mass of calcium nitrate and barium nitrate. Check it for yourself. Take 2 grams of both and figure out the moles. This is going to have more moles. Why? Because less MR, moles and MR inverse proportion. So option B. Equation 1 and 2 show different reactions of halide ion Q negative with concentrated sulfuric acid. What is Q? Sulfuric acid plus this produces HQ, and then sulfuric acid reacts further with it to produce SO2, Q2. It can either be iodide or bromide because you know chloride, sulfuric acid cannot oxidize chloride. It cannot make chloride lose electrons. Why cannot it oxidize chloride? Because it's not a good enough oxidizing agent. It can oxidize bromide, it can oxidize iodide to form sulfur dioxide, but not chloride. What happens when iodine solution is added to a solution of sodium bromide? Iodine, sodium bromide. Bromide is more reactive, so iodine cannot displace it. So no reaction is going to happen, right? Which statement is correct? Nitrogen is unreactive due to the absence of lone pairs. No, it's unreactive because of the nitrogen triple bond that's present over here. That's very strong. Aqueous ammonia contains both ammonia and ammonium. Yeah, the ammonium ion is a branched. Yeah, that's correct. Ammonium ions are bronzed-Lowry acids, and ammonia is a bronzed-Lowry base because ammonia accepts a proton to form ammonium. That's correct. High temperatures are needed to supply energy to break the strong double bonds. No, they're triple bonds in nitrogen molecules, not double. Atmospheric SO2 reacts with unburned hydrocarbons to form a component of photochemical smog. That pan-peroxyacetyl nitrate is formed by nitrogen oxides and hydrocarbons, not sulfur dioxide. When dry ammonia and hydrogen chloride gases are mixed, okay, so you have ammonia and then you have HCl, a solid white ionic compound is formed, ammonium chloride. Which statements are listed? The formation of ionic compound is a redox reaction. It's not redox. Look at the oxidation number of all things. It's not going to be changed. During the formation of the ionic compound, the H and H bond angle increases. Yeah, that's correct, because from ammonia, you're basically going to ammonium. Ammonia has a bond angle of 107 because of this lone pair pushing down, but for ammonium, the bond angle is going to increase because now you have this dative bond here. And when you have this dative bond here, now it's going to be a tetrahedral structures with 109.5 degrees bond angle. So it's going to be, which statement is correct? Only statement 2 is correct. The diagram shows the skeletal formulas of the isomers of C6H12O. Which statement is correct? 1 and 3 are chain isomers of each other and positional isomers of each other. Okay, so we are saying that 1 and 3. So we're going to draw the structures to figure out 1, 2, 3, 4, 5, 6. So this is heptanal, right? CH3, CH2, CH2, CH2. And 3 is 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4. And this is 2-methyl pentanal, right? Because on the second carbon we have a methyl and that's pentanal. So 1 and 3 are chain isomers of each other and positional isomers of each other. They're chain isomers but not positional isomers because the position of the functional group is not changed, right? You are not changing the position of your functional group. Your functional group is your aldehyde functional group. That's not changed. Despite it's a chain isomer, it's not a functional group isomer. 2 and 3 are functional group isomers of each other. So 2 and 3. So let's check option number 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. CH3, CH2, CH, CH3, double bond O, and then CH3. So that's 1, 2, 3. That's 3-methyl, 1, 2, 3, 4, 5 pentane, 2 on, right? And you can count the number of atoms in 2-methyl pentanal and 3-methyl pentane 2 on. They're same number of atoms, so they are indeed functional group isomers, because over here you have a ketone functional group, over here you have an aldehyde functional group of each other, and both have chiral center. Over here, if we figure out this carbon, is it a chiral center? Look over here. On this side we have this chain, this chain, this chain, and this chain, and then a hydrogen. Yeah, this yellow one is a chiral center. Over here, let's figure out. This yellow one is going to be a chiral center here. Look it for yourself. this CH3 attached here, this thing attached here, hydrogen attached below, and this C double bond OH. So this seems to make sense, but we're going to read other statements as well. 1 and 4 are functional group isomers of each other. So 1 and 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, they're functional group isomers because that's an aldehyde and that's a ketone of each other. And both have chiral center. They don't have chiral center. They cannot have, because look, I'm drawing the structure for you guys. CH3, CH2, C double bond O, CH2, CH2, CH3. Check it for yourself. No chiral center here. Now for this one, check it for yourself. In this entire structure, you cannot find a chiral center. If you think this carbon it's double bonded to an oxygen. And you know, carbon-oxygen double bond makes no sense to be a chiral center. 2 and 4 are position isomers. 2 and 4 are position isomers of each and functional group isomers. They cannot be functional group isomers because both have a ketone functional group. The skeletal formulas of two compounds is shown. So we have this progesterone and testosterone compounds. Which statements about progesterone and testosterone are correct? They both contain a ketone group and they both have the geometrical isomerism. So they both contain a ketone group. This is a ketone group, this is a ketone group, okay. And both have geometrical isomers due to the carbon-carbon double bond. Geometrical isomer here and here. For that we need two different groups, but we're in a ring. And in ring, for geometrical isomers, that's not the condition. So we're going to look at this at the end. Let's look at the other one. They have the same molecular formula and they both have geometrical isomers. They have the same number of chiral carbons and they have the same molecular formula. I don't think they're going to have the same molecular formula. Just kidding. We're going to calculate it out. They have the same number of chiral carbons and they both have a ketone group. So first, let's figure out the chiral carbons. This carbon's chiral, 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 chiral. So we have 1, 2, 3, 4, 5, 6 chirals here. 1, 2, 3, 4, 5, 6 chirals here. 6 chirals here, 6 chirals here, right? And then says they both have same chiral carbons, done. They both contain ketone group. This ketone group here, this ketone group here. I didn't even have to calculate the formula. Now let's check we're right. Look, I just went with the easiest option which I could, because I thought that if I had to calculate the molecular formula, I would have to calculate the carbons and all this stuff, so I missed it all. That's how you play smart. Which intermediate ion forms in the greatest amount during the addition of HBr to propene? Propene, CHH, CH double bonded, C, and then an H, and then an H. Now you know that when we're going to add HBr, since we know this bromine is going to attach to this and this hydrogen because it's electrophilic addition, firstly the electrophile, which is going to be this, is going to attack over here. Is going to be attached over here, since this pi bond is going to attack on the electrophile, whatever, and then H is going to be attached here. Since H is going to be attached here, this double bond over here is going to be broken and then a positive comes here. So that's CH3, CH positive. Over here the bromine is going to come and attach. Why? Because the bromine is going to attach towards the carbon that has less hydrogen, and this is the carbon with less hydrogens, and then CH3. So that's the answer. Two hydrocarbons, RCH3 or not CH3, reacts separately with bromine in the presence of ultraviolet light. One of these hydrocarbons is unsaturated. That means has a carbon-carbon double bond. So out of this chain and this chain, we need to figure out which chain is going to be unsaturated, because in the question they're asking a propagation stage for the saturated hydrocarbon and a termination state for the unsaturated hydrocarbon. So let's figure out. For that, we would have to draw the structures. We have a CH3 and then we have a CH and then a C. There's a CH, or is this, and then you know that there's a CH3 attached to it at the end. So CH3, and there is a CH3 over here, right here. So this definitely, the R is gonna be the saturated one. As you can see, there's no carbon-carbon double bond. For the second one, let's check out this. Then there is a CH3, and then there is a CH between this hydrogen. Okay, so no, there was an extra carbon here. No, this one's unsaturated. Just realized this thing, that there was a carbon here and then a CH3 here, and there's a double bond here and then a CH3 here. So this one was unsaturated. Sorry, just missed out this thing, the last one. And over here, this one is CH2 and then there is a CH3. So this one, second one, R naught, is your saturated hydrocarbon. Now a propagation state for this saturated is R naught. So cross, and we're looking for a propagation. In propagation, a normal molecule is going to react with the free radical. So this is correct. This is wrong because you just have a free radical. And over here, termination stage for the unsaturated. So I don't know it's correct or not, but yeah, two free radicals reacting together. So that's going to be the termination step. So over here it says that the fumes from the exhaust of petrol burning cars contain the following pollutants: unburnt hydrocarbons, nitrogen dioxide and carbon monoxide. Which pollutants are removed by oxidation in the catalytic converter? Unburnt hydrocarbons are basically oxidized to form carbon dioxide and water. Nitrogen dioxide is not oxidized, it's reduced to nitrogen, and carbon monoxide is oxidized to carbon dioxide. So over here, oxidation only occurs in unburnt hydrocarbons and in carbon monoxide. So 1 and 3 are oxidized, and nitrogen dioxide is reduced to nitrogen. Compound XC7H11ICl2 is dissolved in ethanol in sodium and mixed with warm aqueous silver nitrate. So over here you can see we have an iodide and we have two chlorides over here. So this is a halogenoalkane, and then it's dissolved in ethanol and we're adding silver nitrate to it. A precipitate is seen immediately. What is the color of this precipitate and what is the structural formula of the first organic product? First things first. Now either a precipitate can form with chlorine, that's going to be white in color, or iodine, that's going to be yellow in color. But over here there's a carbon here, a carbon here. So you know that carbon-chlorine bond is stronger, whereas carbon-iodine bond is weaker. Why carbon-iodine bond is weaker? Because the bond length is greater. So this bond is going to break off first. Carbon-iodine bond is going to break off first. So since carbon-iodine bond is going to break first, so iodine is going to form a precipitate with silver nitrate first. So the color of the precipitate of iodine is yellow. And the second, when iodine is going to break off, OH, since we're dissolved in ethanol, OH is going to substitute and take its position. So it's going to be option number D. 1,4-dibromobutane reacts with an excess ethanoic sodium hydroxide until no further reaction takes place. What is the relative formula mass of the major organic product? So you know that we have 1,4-dibromobutane. So 1, 2, 3, 4 carbons. On the carbon 1 and carbon 4, we have bromine, and then reacts with excess ethanoic sodium hydroxide. When we are dealing with ethanoic sodium hydroxide, what happens? Elimination takes place. So this bromine is going to be eliminated from here. This bromine is going to be eliminated from here, and we're going to form a carbon-carbon double bond. So one double bond we are going to form here, and one double bond we're going to form here, and then remaining places, let's fill them with hydrogens. Until no further reaction takes place, what is the relative formula mass of the major organic product? Now what do? You calculate the mass of this product. You have C4, 4 carbons, and H is 1, 2, 3, 4, 5, 6. H 6. So that's 48 plus 6 equals to 54, right? So over here, option A is going to be our answer. A small reaction of a polymer produced from 2 monomers is shown. What are the 2 monomers? So we're going to draw this polymer and then we're going to figure out. So firstly, we have H, and then we have a CH3 because it's 2 times, and then we have a CH CH3, and then we have a CH and H. So now in order to know the monomers, what are we gonna do? We're gonna break the extension bonds, and we're gonna break the center bond and make a double bond between the carbon atoms. So break this, and now add a double bond here, add a double bond here. Check out what polymer is what monomer is this and this. So over here we can see 1 carbon, 2 carbon, and 3 carbon, and there's a double bond. So this is propene. This structure right here represents propene, and this structure right here represents, if we consider this as the longest change, on the second carbon we have a methyl, so that's 2-methyl propene, right? On the second carbon we have a methyl, so that is 2-methyl propene. Even if you don't write this 2, it's going to be fine, because there's no other option for methyl to grow, because if methyl comes on this terminal ends, it's not going to be considered methyl, because you can't have methyl on terminal carbons, right? So 2-methyl propene and propene, which option chose this? Not this, not this, this. So option number D. The balanced equation for the reaction of X with excess acidified K2CO2O7 is shown. Compound Y is the only organic reaction product, so compound Y, and then we have 1 mole of water. Which compound is X? So we're adding 3 moles of oxygen for the oxidation to form 1 mole of water. So let's add 3 moles of oxygen. Let's see how are we going to oxidize A. So if we oxidize A, we can see A is a aldehyde. So there's going to be an OH added here, and then we're going to add an OH here, because this is an aldehyde. We need to convert aldehyde to alcohol. For that, we need to add a O over here and O over here. So that's going to form a alcohol carboxylic functional group. We need to convert aldehyde to carboxylic acid. And then I can see an alcohol here. To convert alcohol to carboxylic acid, I'm going to add a double bond here. I know I need to remove some things as well, but right now I'm just considering that how many oxygens am I adding? I'm adding 3 oxygens to oxidize this thing. Now let's see what kind of things am I removing. When I'm going to, obviously I'm going to oxidize it. What kind of things am I going to remove? From here, I'm going to remove this H. From here I'm gonna remove this H, and then what else can I remove? Let's see. I have to fill the valency of the carbon. So 1 2 3 4, 1 2 3 4, and then this carbon is making 1 2 3 4 5 bonds. It cannot make 5 bonds. This is a tertiary carbon, not to carboxylic acid. It is going to oxidize to a ketone, so I need to remove this H out from here. Do you get this? I need to remove this H, and then I'm going to form a ketone over here. That's the trick. So look, now I'm using exactly 3 moles of carbon. 1 mole, 2 mole, 3 moles for one compound. So it's going to be Y. Definitely this. It's going to be Y. So I think it's going to be option A, because I'm using 3. But over here, I'm again going to do that. If I oxidize this thing, I'm going to form 2 H's. And then over here as well, if I oxidize this, I'm going to form this carbon. I'm going to form 2 H's again. That's going to be a lot of H's. I can only form 1 water. Not possible. If I oxidize this, I'm going to form OH, OH, and OH. But you got to realize I got to have 1 water formed as well. Over here, I don't have any water being formed, right? This structure number C double bond. If I oxidize it, I'm going to get a C double bond O, and then I'm going to remove this H. I'm going to get a ketone here, and a C double bond O here. Remove 2 H's. Not possible. I have to add 3 oxygens. So it's going to be option number A. three mixtures are heated under reflux, which mixtures will produce sodium propanoate? So over here we have 1, 2, 3. We have an aldehyde and we're reducing an aldehyde. When we reduce an aldehyde with NaBr, we form alcohol. And which alcohol are we going to form? We're going to form propanol, right? Over here we have sodium and we have 1, 2, 3 propanol. Sodium and propanol is going to give sodium prop oxide. Sodium prop oxide is going to be the alcohol plus hydrogen gas, not sodium propanoate. With your alcohols, what you form? You form prop oxide, you form methoxide, you form ethoxide. Why? Because you have a single O here. With acids, you have a double O. Then you form sodium propanoate, ethanoate, not with your alcohols. Here we have a nitrile and we are doing alkaline hydrolysis. When we're going to do alkaline hydrolysis, first things first, we're going to form an alcohol, CH3, CH2, COOH. This nitrile part is going to convert to alcohol, and then this sodium is going to react with this alcohol, and then it's going to displace this H. Sodium is going to come here, and then sodium gets a positive and this gets a negative, and we form sodium propanoate. So only in reaction 3 we're forming it. Over here I told you we're going to form prop oxide, over here propanol. Okay, which compound is a product of the hydrolysis of this thing using aqueous sodium hydroxide? So we break it from the center. First let's make it CH3COOCH2 C2H5. We break it from the center. We know that this part is the acid part, so we have this part as the acid. That's what kind of acid is this? This is ethanoic acid. We have ethanoic acid, so we're going to form sodium ethanoate. This ethanoic acid is going to react with sodium hydroxide, so we're going to form sodium ethanoate, which is this, I guess, because that's one. That's wrong, something wrong here. That's oxide. There should be 2 oxygens over here or something else. C2H5, then 3 carbons. No, we need ethanoic acid. So that's how we deal with it. Compound Q reacts when heated with HCN in the presence of catalyst to produce compound R. So compound Q reacts with HCN to form compound R. Molecules of compound R each contain 4 carbon atoms. So initially we know that Q is going to contain 3 carbon atoms, and then it's going to react with HCN. A carbon is going to be added, and then compound R is going to contain 4 carbon atoms. Okay, what is compound Q? Compound Q should contain 3, then HCN going to be added to it, then it contains 4. So over here, firstly we realize that this is a chloride and is heated with HCN in the presence of catalyst, not this, because that's heated with NaCN or KCN, halogen or alkanes. This is a carboxylic acid. We don't do nucleophilic addition in carboxylic acids. We don't do nucleophilic addition here. So we're going to do nucleophilic addition either in this or this. Now we got to check out the number of atoms. This has 1, 2, 3 carbon atoms, and this is 1, 2, 3, 4 carbon atoms. We don't need 4 carbon atoms. We need 3 carbon atoms in compound Q, so then it can later react with HCN to have 4 carbon atoms. The table shows the reagents and products. The 3 reactions which rows are correct. Ethanoic acid plus sodium carbonate, sodium ethanoate plus water plus carbon dioxide, correct. Ethanoic acid plus magnesium, not water. Acid plus metal gives salt plus hydrogen gas. Ethanoic acid plus methanol, there is sodium, there should be methyl ethanoating form and water should be formed, right? And this is correct. This is methyl, this is the ethanoate part, and then this is water forming. So that's esterification reaction happening. Okay, 7 aldehydes and ketones contain only 1 oxygen atom per molecule, have 4 or fewer carbon atoms in their structure. So we have to draw all the aldehydes we know that have fewer carbon atoms. So firstly we're going to draw methanol. Okay, then we draw ethanol, then we draw propanol, and then we draw butanol. So these are all the aldehydes that could be made that have fewer than 4 carbon atoms. Alkaline I2 is added to each of the carbonyl compounds. Which of the carbonyl compounds produce a yellow precipitator? To check that, we need to draw all of them. And then we draw all the, what are they called? Ketones. So ketones, there cannot be a ketone with 2 carbon, you know. So we can only have ketones with 3 carbons. So this ketone is possible, and then we have this ketone possible. So these are all the structures I could draw. Now out of them, how many of them are going to react with alkaline I2? The structures that have C double bond O, CH3 are going to react. So we are looking for this group. So over here, I cannot, in the first one, I cannot see this group. In the second one, I can see this. In the third one, I cannot see it. In the fourth one, I cannot see it. In the fifth one, I can see it on both sides. In the sixth one, this one, I can also see it. So there are in total 3 structures that are going to give me a precipitate. Over here, if you might think, but they're just carbon attached to 2 hydrogens. We need carbon with 3 hydrogens on the other side. So there are only going to be 3 structures. Some properties of compound X are listed. 1 mole of X reacts exactly with 8.5 mole of oxygen when completely combusted. X does not react when heated with acidified KMnO4. So X cannot be what do we call, oxidized. So this is a tertiary alcohol, it cannot be oxidized, so we straight away cross it. Second, this one right here is also tertiary alcohol. X does not. We don't cross it, we circle it, because that's what we're looking for. So this and this, and this is going to react with KMnO4, so we cross it, right? And this is a ketone, so this also does not react. So we have 2, 3 and 4 which we need to check. So now we got to make their equations and balance them out. 1, 2, 3, 4, 5, 6. So C6H is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6H12O plus oxygen is going to give me 6 carbon dioxide plus 6 waters. And now if I try 2, 6, 2, that 12, and then I get 12, 13, 14, 15, 16, 17, 18, 18 minus 1 oxygen here, 8.5 here. Tick. 2 is going to be correct. Now I check for 3. 1, 2, 3, 4, 5, 6. C6H is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14 and O. This cannot give me. You can see it. When I balance this, I get 8.5. When I'm going to balance this, I cannot get 8.5. Cross. Now for this, 1, 2, 3, 4, 5, 6. C6H is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then O. You can see it for yourself. Same molecular formula of this thing and this thing. So when I'm going to balance this thing as well, I'm going to get 8.5. And I need exactly 8.5. So it's 2 and 3 that's giving me 8.5. Okay, a sample of magnesium contains 24, 25, 26 magnesium. Only the percentage abundance of 25 and 26 is the same. The relative atomic mass, if the sample is 24.3, what is the percentage abundance of Mg24? I can do it mentally. 25, 26 and 24. 25 and 26 are in equal amounts. So over here it's 25.5. Wait, over there it's 24.5. Let me do it mentally. Now the answer is coming out to be 24.3. So what do? 24x plus 25.5 times 25.5 times 100 minus x upon 100 equals to 24.3. 24x plus 25 minus 25.5x equals to 2430. 24 minus 1.5x negative, and then this goes on that side, becomes negative 1.5x equals to 2430 minus 2550. 2430 minus 2550. 2430 minus 2550. 120. 120. 80%. Do we have an option that says 80%? Yeah. What I did was simple. Took 25.5 as one of my percentages because I knew 25 and 26 are in equal amounts, so it's going to be exactly in the center. And then took 24 as 1. So 24 multiplied by x, that's going to be the abundance of 24, and then 25.5 multiplied 100 minus x, the abundance of the 25th isotope, whatever this isotope was. And then it was a combined of this and this, right? And then I just solved the equation, and it was 120, negative 120 equals to negative 1.5x, x equals to negative 120 upon negative 1.5, positive, positive, 1 times 80 times x equals to 80. It was a simple like maths problem.